autoregressive flow, and 5 different sandwich basically of reverse permutation. So there were 10 of them. We added them all on top of each other, and then you see the relation. You see the modeling is quite good, but there's still like a little bit of dot which is connecting to them here and there. So I think we already kind of were talking before, like why we see that. But anyone here has any idea, like why? Do you think, first of all, is there a way we can remove all the blue dots between the two black? Or other option is you believe that fundamentally it's not possible because it's a normalizing flow. Good plots. Okay, let's see. Very good. They're very good. Yeah. Yeah, yeah. Like this is pretty good. Like this one. Okay, so pretty good. I think most of you got it. So in principle, since these are all continuous functions, it's a little bit difficult to get 100% aligned with these black dots. But then if you push enough, like what we see here, you actually can get quite reasonable performance. I think Ritesh, who is Ritesh? Okay. How many layers do you add? 5? Huh? 1,000 epochs. Okay. What? Yeah, so I think in general people are getting good stuff, so it's good. It seems like you guys are folks are enjoying here. So what we need to do one last thing is like we want to see so far as this written here, we are mostly doing it like in a quite black box way because we are using our wrapper function. What we want to do here, we want to print the steps, like how things are changing when you're doing the transformation. So we are doing, for example, for my case, I'm doing, there are 5 of them on top of each other. So I'm doing like 10 transformations. So we want to see how things are changing as you are transforming your X. So let's run this cell and see what it's printing. Is it gone? There's some connection issues, so I'll just wait. You carry on. Basically, continue checking this 2F. The goal here is to print every step and see how things are changing. I'm just restarting my Jupyter, but you carry on. So the next in the next cell, the goal. So let's say if you have 10 steps, I want you to print 10 pictures, such that you can see how things are changing. So you need to write a little loop there.
Whatever, I generated 10,000 points, and there's a smooth connection.
Smooth connection.
Still,
Interesting.
so it
That
learns
is fascinating. Yeah. So there's a tiny little bit.
which is going smooth.
Could you post it to Slack so everyone can see?
But this is like 10 layers or 6 layers.
This वही 10 जो तुमने किया,
हाँ.
300 epochs.
हाँ.
Okay, and but sample generated is big.
Okay.
Much bigger.
If you get more samples, then it's a smooth connection.
Yeah, because there is this non-zero power problem.
I think yeah, this is probability low. I think. Yeah, I don't know. Did you generate? What's that? Ritesh, did you generate more samples? Huh? How does it look? Exactly same. Alright. So, I mean, this cell, the 2F, it prints just one step. So what you need to write here, you need to add your code here. Just write a little loop. You see everything here, write a little loop, and then write the loop such that it prints the number of, whatever number of steps you have, it prints that many pictures on the screen. Okay. So we have enough information written, in the code, so you should be able to. So this is kind of gives you the number of steps that we need, and flow underscore transform. That gives you the total number of transforms that you have defined with your flow object. Essentially, you have to write something similar to that. Oh, yours is not bad. Why so bad? Okay. Okay. And if you go to all the steps, step by step. Oh, are you not printing everything, or because it should print at the end? Look at that. You can print the total number of transformations. No, don't change there, but then you can change, you can write a loop which runs through the number of transformations. Range 8, okay. Okay. But you're not printing everything because the last go up, or the last picture should be this. It is. So from the flow object, see, look at this thing. This should give you the total number of. So that's that plus one. Yeah, that plus one. That many loops you have to run. I'm showing that one on the screen. You can also have a look and modify your code based on that. But anyways. Are you able to print? Yeah, it's printing, right? Good. Huh? For loop হচ্ছে তো নাকি?
কেন দুটো লাগছে কেন? আমার কি 5 ট্রান্সফর্ম হয়।
হ্যাঁ।
আমি তো মানে তো এটা হচ্ছে অ্যাকচুয়ালি আসলটা যে এটা ওখানে ছিল অলরেডি।
হ্যাঁ।
তো এর মধ্যেই তো আমি 5টা আমি এর মধ্যেই প্লট করতে পারি।
কত তোমার কি 5টা আসলো মানে 10টা?
আমি 5টা করেছি। কিন্তু এটা কি করছে?
না, কিন্তু তোমার এইটা যেটা দেবে সেটা হচ্ছে তোমার এখানে যত করে লিখেছো তুমি, এই যে লিখেছো একটা দুটো দুবার করেছো, একটা দুটো তিনটে চারটে হবে এটা। হ্যাঁ, চারটে হবে ওটাতে।
আচ্ছা,
তোমাকে
কিন্তু আমি বলছি আমার থেকে 5টা আছে, আমার থেকে 5টা প্লট আসার কথা, তাই তো? 5টা ট্রান্সফর্ম, প্রত্যেকটা ট্রান্সফর্মের পরে আমি একটা করে প্লট পাওয়া উচিত।
হ্যাঁ।
আমি এটাকে জন্য ইয়ে করে দিয়েছি পরেরটাতে। আমি যে 5টা ট্রান্সফর্ম লাস্ট ইজি ফ্লো ডিস্ট্রিবিউশন স্যাম্পল লিখেছি, তাই মানে আমি
না, এবার তোমার হচ্ছে ফ্লোটার মধ্যে কতগুলো ট্রান্সফর্ম আছে সেটা এইটা থেকে জানতে পারবে। অলরেডি ফ্লো মডেলের মধ্যে আছে।
আমার ফ্লো মডেল আছে, এখন আমি এটা বলছি যে নাম্বার অফ ট্রান্সফর্ম
এই ট্রান্সফর্মারটা তোমার ইউজ করছে
না, মানে আমি যেটা করতে চাইছি সেটা হচ্ছে আমাদের ডিস্ট্রিবিউশন নাম্বার 1,
হ্যাঁ এক্স্যাক্টলি নাম্বার 2 নাম্বার 3 করে 5টাতে আসতে আছে। হ্যাঁ হ্যাঁ এক্স্যাক্টলি।
তার জন্য আমাকে আগে থেকে এটা কেন
এখানে স্যাম্পল বানাচ্ছে, এখানে কি এখানে তোমার প্লট তো আসছে।
আমি প্লট আসছে, আমি শুধু এটাকে ই করে দিয়েছি এন ট্রান্সফর্ম। আমি এটাকে আমার করা উচিত হচ্ছে এন ইকুয়াল টু ট্রান্সফর্ম সামথিং, এখানে আমি 5টা করব, এখানে 4টে আসছে, এখানে ডাবল লুপ।
হ্যাঁ,
দুটো লুপ চলছে,
একটা লুপ চলছে তোমার এর জন্য টর্চ নো ক্যান দিয়ে একটা ওটা জাস্ট নরমাল লুপ, তারপরে তোমার লুপ সেকেন্ড কি ও দেখে দাও। अच्छा 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 गुड, तो कनेक्शन आ रहा है। So I guess like we need to move. Did you get some plots? Otherwise, you can also try later. One last thing we wanted to talk before we move on. So we have seen, like, even though you generate pretty good, like there is some, if you start generating more and more samples, there would be some sort of connection between the two hubs. If you simulate more events, it's just because of the reason, although Flow is doing a very good job here, you mostly are able to differentiate between the two hubs and model very well. Another approach one can take is using a conditional generative flow. I mean, conditional generative algorithm can be used for any other architecture, like for VAEs, you can use condition. For GANs, you can use condition. For flows, also you can use condition. So we are showing you some examples here where we are using conditional flow, and you'll see how things change quite a bit just by using a conditional flow. So what we are doing here, we are again using the same moon data. So you see, like, we're getting the same make moons from the data sets coming from scikit-learn. And this time we have a label variable. So these labels will be, I mean, if you print the labels, you'll see how they look like. But as you could see here, what the way we are plotting, we are taking the moon data set, the first column, and we are printing essentially two chunks, like 0 and the label equal to 0 and the label equal to 1. So that's the second line. And all the level 0 points are plotted with orange dots. And all the level 1 points are drawn in green. So in this two-dimensional distribution, we are just separating out. So the first hub and the lower hub, they have been already labeled as 0 and 1 in the original data set. So that's what we kind of already stored now from the original data set. Previously, if you remember, we were not looking at the second variable. So what we were doing, we were just taking, we were just taking the x moons, and then second variable were, since we didn't want to store it, we were just not storing it in a particular way. And we were plotting all of them, 0 and 1. We were plotting all of them together with the black dots. So it's just everything, all the dots. Now this time we have separated them out based on whether they belong to the upper hub or the lower hub. So that's the orange and green. Okay, so maybe run that cell, and now what we want to do, we want to train the flow, the same flow, using the condition. So we want the flow to know whether it's looking at the upper hub or the lower hub. How we do here, it's written in the text here. The conditional model in flows are handled via this context argument. So this inflows package, they have this context argument, and you see here the context feature is equal to 1. So everything stays same. We have again the transform list. Features are again 2. In layers, you can choose whatever you want to. We are using this masked autoregressive transform that we have been using for some time now. And then the only additional parameter is this context feature 1. And we are using a series of, so there are 10 of them. 10 of them are added together, the masked transforms, masked autoregressive flow transformations, and then we added one reverse permutation. Then we combine the transforms, and then this time we, again the same way, we pass the transformations and the base distribution, which is the standard normal of shape dimension 2, to the flow, and that's how, and then again define the optimizer and train it the same way that we did before. The only difference would be notice the log likelihood. I'll just open another notebook beside the other side, and so that you can see them side by side. The log likelihood last time we calculated in above was NLL equal to negative flow dot log probability of x. This time we are doing the same, we are calling the same function, but we are calling with x and the y conditional value. So that's the only difference that we are making in this implementation. So now we have already marked the note the context argument here. After that, the optimization is the same. Okay, so run that cell and see what you get. So essentially, the problem stays the same. We reinterpreted the problem based on the upper hub and the lower hub of the moon, and we're training a network which is now aware of the fact that the two sides of the distributions, points in the two part of the distributions are different. Okay. So in my case, I trained for 20 epochs, and this is done. Let me see how it looks like. It looks okay, but take 5-10 minutes. Do use more epochs, but in the meantime, if you have any questions, we can discuss here as well. But at the same time, please keep trying. Huh? The motivation is that we have the two sides of data set. Now it was for the continuous function, it was becoming slightly challenging to model it. Now if we can just identify the points which are in, because these two sides are disconnected, if we can identify the two sides, the points belonging to the two sides, and label them, it just becomes, and then we condition when the flow is learning. So meaning the flow is learning, one time the flow is learning the upper hub, other time is learning the lower hub. It just becomes for the flow to learn it easily. That's why we're doing it. And it's a very simple problem, but in reality, you will have this kind of problems. And I think there is some text written here.
The other thing is that if you actually want to use a flow for physics simulation, you are going to
Yeah.
using it for shallow simulation. Is going to be the properties of the particle. Condition on that, you will make the shallow. So you need to definitely know how to condition for that. And for GANs and VAEs, it's straightforward. For flows, it's a bit tricky because the network is not directly. The input is always Gaussian noise. You don't put anything else as input. So it comes in as context. So yeah, that's useful to learn how to condition.
Yeah, so whatever Vaishik just said, it's written here in under 2G. You can read it later, but the same concept. Yeah, but thanks. Yeah, because no, it's good. Yeah, so I guess you get some motivation. I think calorimeter simulation that Vaishik also works, and it actually becomes quite essential because it depends on the energy of the particle, the shower shape, and everything. Conditional. I think you also use conditional. Huh?
20 to 50 epoch, there was not much difference.
In this conditional thing? Let me try also training. But also we can use more layers, right?
He didn't learn.
So what happened?
So they put 100 layers he did.
Oh, 100 layers. Okay.
उसमें क्या होगा? Yeah, vanishing gradient can happen.
Or-
It's okay. It's possible vanishing gradient. but
Could
I'm
be the
not
negative.
100 is already
What-
you
Does
need
it
to reduce
throw you
vanishing
any
gradient.
error?
No, it doesn't throw me any error. इतने सारे वो flat
Yeah.
है उसमें उधर जाके कुछ भी change करो इधर कुछ नहीं फर्क पड़ता.
100,
Yeah,
100,
I've never
100 steps. So we're using 100 steps there, right?
100. What I would try is that more epochs with less.
Yeah, yeah.
That's
Just
right.
train a little bit longer rather than.
Already the default was 10 layers. मुझे 10 जरूरत है क्या?
Oh, yeah.
हो गया. Yeah.
5 में काम चल रहा था ना पुराना वाले.
और पहले 5 हाँ 5 पे चल रहा था.
हाँ, अभी 10 20 हो गया बेसिकली.
So I guess I've never tried to make a gigantic flow, but it could be that. But you can just reset and try.
Let's maybe. Okay, so I think we should move on. So you keep trying this on your own time later on. There is one last exercise. You can do it later. The idea here is that after this training, you need to just plot. So this is the basic plot that you have. The exercise below here is that you need to just plot them, the two moons separately in the two different colors that we did at the very beginning, orange and green or whatever you choose. There's also a bonus task that you can try it later. We don't want to spend too much time here because we need to have a little bit of some more discussion that we want to do. So Aishik we'll just move to the slides for next half an hour or so to show you some applications of GAN. Oh, sorry, not GAN. Applications of generative algorithms in general in particle physics. So Aishik will go through that. But before that, if you have any last things you want to discuss, we can have it now. Otherwise, we'll move. Right?
Even while I'm talking after that, I think we might have some time to discuss.
Yeah, we will have we have time till 5 o'clock.
Okay. Cool. have the slides? Ah, nice. Did you have it at some point, or did I misplace it?
Anyone has the pointer?
Wow. How did it reach there? Thank you. Yeah. Okay. All right. Yeah. So we've learned about a few different generative models. The one we didn't do was score-based models because they're really like big and difficult to train. I mean, not difficult, just resource intensive. So you definitely need GPUs to train them. But yeah, hopefully you've got the context of how to basically how to train generative models. And normalizing flows are really nice for physics data sets. You can continue to play with them while, with your notebook while I give you a little bit of context of like the biggest application of generative models in LHC. I mean, the one that really motivated everything was Halo simulation. So let me talk a little bit about that. So this is the motivating plot we keep showing. This is one from Atlas, which shows that there is a lot of demand for our CPU resources, and that is, whenever we make this plot, like the future looks very scary. That like the demand is far higher than the supply we're going to have. So we always need to optimize our algorithms such that we can actually do our do the physics we want without, I mean, yeah. I mean, uh, so to do that, we need to see where are we using most of our CPUs and see if we can find better algorithms. At least for Atlas, a large chunk of the time goes for simulation. In fact, 75% of that goes for Calo simulation alone. For the other experiments also, Calo simulation is, I mean, for Atlas, it's a serious problem, but for the other experiments also, it's usually one of the largest consumer of CPU resources. So what happens in a calorimeter? You have something like a pion or a photon in this case that enters your detector, and as soon as it passes through the active material, it starts to shower, right? So when you're tracking this using your extremely precise simulators like Geant4, it's going to start tracking each of these particles and how it passes through, when it converts a photon into 2 electrons and so on. And it can get very expensive to track all of these particles as they pass through the calorimeter, right? And in the end, what you record are just images, 3D images. You do not record the time evolution of the shower. So the question is, can we not take a shortcut and go from the properties of the particle directly to the images and skip the time evolution? This is what people have been trying to do well before machine learning and deep learning became popular. We used to come up with hand parameterized methods to go from here directly to here, and it's a lot of work. It requires a lot of postdoc students to come up with these kind of parameterizations, and you have to, what you do is, at least in Atlas, we save a lot of these histograms from our Geant4 simulators in the memory, and then we sample events from these saved histograms and so on. So it's both, so first of all, it takes time to tune, and it's very memory intensive. And the hope was that maybe you can, now that we have all of these models that can not just draw pictures that it's seen before, but like can start to draw very interesting images. I hope you're starting to see the message in each of these AI generated images. Right, so it can do cool things, and it can learn from different parts of the phase space and generate new images in an interpolation region where it's never seen training data before. Like it's never seen training data like this. So yeah, okay, you know about VAEs and GANs. I'm going to skip that, but these were the first generation of deep generative models that were tried for Calo simulation. And the very first paper was the CalOGAN. This is really that got the ball rolling. And not just in terms of showing good results, but they actually did something very impressive is they wrote up a Geant4 tiny detector where they could simulate single photon showers. And then this data set is being used till today to develop new kinds of generative models. So I would say even more than actually showing that GANs can be used for simulation, the biggest contribution here was making this publicly accessible data set. So this was 2018, I believe. I don't think I've written down the year, but yeah, 2018. And within a year, Atlas had put out publicly the first results of GANs and VAEs that had been, I think this was just the GAN, that had been integrated into the simulation software. And so you could actually make comparisons of Geant4 to the baseline fast simulation method to these neural networks. And then you could say things like, compare speed and memory. And so we found that, for example, the memory footprint of these generative models was at the order of megabytes, whereas the baseline fast simulation was at the order of gigabytes. So we were doing much, much better in memory consumption. And in speed, basically a deep neural network is way, way faster than Geant4, especially because Geant4, the speed climbs as the function of the energy of the particle, whereas for a network, it's the same regardless of the energy. And then we also wanted to look at things like interpolation tests. So if we only have training samples at like, let's say, 32 GV and then 64 GV, and then you want to check if it can also generate samples where it has never seen training data. And so we managed to show this. So the black here is Geant4, and the red is the GAN. And this is some high-level observable that was not, so the GAN is only trained on raw images, right? It doesn't know anything about what observables you construct from those images. So we managed to look at this one. This was never even looked at during the model optimization phase, but nonetheless, the GAN reproduces it well, not only in the training energies, but also at this interpolation region. So this was a very promising thing, and it was studied fully inside the experiment, so it was apples to apples comparisons. So it was a very nice thing we saw. In fact, this was my PhD, part of my PhD work. So then the challenge was this entire study was done in a very small region of the detector. So one tiny slice. And then when you want to apply this on the entire detector, we realized that there are some problems. So these are different layers of the calorimeter that we're showing. They're actually one in front of the other, but we're showing them next to each other just to show you the geometry issues. So each of them, the cell sizes are different and their alignments are different. So for the same position in the, so we're cropping these images, right? But for the same position in the middle layer, the front layer can have different configurations. So here, if the energy is in the middle, it distributes in the top two cells of the front layer because they're very long and very narrow, right? So long in this direction and narrow in this direction, these strips. So if the shower is centered here, it'll generate most of the energy in the first two cells here. If we're using this configuration, but you could also have this configuration for which the bottom two cells would have this most energy. So exactly the same shower shape will appear different because let's say our camera is different, right? So, and this geometry changes very, very quickly. Like if you change even 0.025 in eta, the geometry completely changes and it can change how the same shower looks. So in the first thing we conditioned on these geometries, in the central region there were about 8 configurations. So like for the same middle layer, you can have 4 kinds of front and 2 kinds of back. But as soon as you want to include the hadronic calorimeter and so on, the number of geometries just explodes. And these kind of discrete configurations are not easy to condition on. So in general, you'll find that generative models and you can condition them, and if you condition them on simple things like, for example, the position of the particle in this cell is a continuous number and it conditions very smoothly. But discrete things like this are quite challenging. So yeah, so you can, and then you can think of even more challenging geometries where the cells are bigger, smaller. All three of these are showing exactly the same shower shapes, all right? The physics is the same, just the cell segmentations in the detector are different and the images can look very, very different. And imagine this one, it's a transition region where on the left you have some geometry and on the right you have another kind of geometry. So one thing that Atlas has put out recently is training hundreds of GANs in different parts of the detector and then validating them. So you can see that like this is just the energy plot at different, and then you have to do this for every GAN for many different distributions. So it's very, very challenging, to put it mildly, and it's not something that hopefully you don't have to maintain hundreds of GANs in your experiments. So the challenge now is, can you somehow come up with an architecture that can handle multiple geometries simultaneously? So all of these kind of geometries. And so the older approach was to say that each of these is a separate configuration and we condition on them. It doesn't scale very well. But intrinsically, you know that the geometry is simple. It's just the width in eta, the width in phi, right? And it's a continuous thing. So we can switch, we can turn a discrete conditioning into a continuous conditioning if you instead condition on the properties of the cell. So that was the idea behind some recent research work where we use what is called geometry-aware learning, where the model is told while it's learning and generating not only the cell it's about to generate, but also the properties, so the position, the size of the cell, and so on. And so for this, you do it autoregressively. So instead of generating them all at once, you start from this cell and then you go to the next cell and so on. So it has an idea of neighborhood. So if the nearby cell has lots of energy, then this cell will also have lots of energy. And also if the cell is bigger, it'll deposit more energy. The cell is smaller, less. So with this, we were able to, for the first time, show that you can actually simulate these kind of transition regions that had never been tried before. So that's a good step in the right direction. And yeah, you can see that, so this is the geometry aware model, and this is Geon 4, and then for different kinds of geometries, you can reproduce these things. In fact, we also showed that these models can interpolate, so they can generate geometries that is never seen in training as long as they're within, the cell sizes are within the range that it's been trained on. So that's nice. And of course, like just to compare to something that's not conditioned on the geometry, it would have been impossible to solve this kind of problem. But with conditioning, you can do it. But there is an alternate way to solve the same problem, right? So what I'm talking about now is geometry-aware simulation. You can have an exact opposite idea, be geometry agnostic. So there, instead of simulating cells, you say, well, the physics is the same, so let me simulate at the maximum precision. So I generate point cloud hits of energies, and then you can cast them into cells however your cells are in post-processing. So that's another approach, and the community in general has been looking into this for a while. Recently, there's been a paper also for point cloud CalOSim, and they in this paper, they compare cells to point clouds, and of course, the point clouds don't do as well, and this is a generally known fact that point cloud generation is one of the most challenging things for generative models in high energy physics right now. So there are several papers, they all show that like they can go up to a certain number of points per image. And this is currently the frontier that everyone is trying to push, to have more and more points and go further low in energy. What that means is, to do these kind of things, you often have to make a cut that all points below this much energy, I will not even try to simulate. So yeah, there are these kind of approximations we're having to make. And hopefully in the next few years, we'll be able to really generate point cloud calorimeter images. And then it'll be interesting to see if in what kind of calorimeter geometry aware approach is better and what kind of point cloud method might be better. So both are very expensive, like the point cloud method particularly is very, very expensive to do. but you can see the physics motivations for it. And so why beyond just like whatever I was talking about in Atlas, why is this interesting? Because even CMS has like these high granularity calorimeters coming out, and people are developing generative models for it. And there are all kinds of different experiments that are coming up with their own generative models. And in each case, you're spending like 2 to 3 years designing these models. If you look at the architecture, each of them has their own unique architecture. I remember the first CMS one has this DC GAN convolutional architecture. This Atlas had GANs and VAEs with dense structure. I can't remember which one Alice had, but yeah. And if you look at the generative models in the industry, they have one model that can one basic architecture that can do everything. Even back in the day, they would have just one convolutional GAN which can do pictures of faces, pictures of homes, pictures of cars. They could handle all of these things. And nowadays, with stable what is it called, diffusion, you can generate everything, right? You can generate again pictures of people or even art, comics. You can do whatever. But in our case, in physics, we seem to still rely on architectures that are super specific to your particular detector. So another thing that we're wondering about is, can we have foundation models? Can we have one architecture that is capable of handling all these different kinds of detector geometries? And so then you can train it on a large data set, and then so it's pre-trained and it's already pretty good, and then every experiment can just fine-tune it into their own detector geometry and get the last precision you need. So that would be an interesting common effort that would, of course, first of all, require you to come up with a common architecture. So it could be either a geometry aware or a geometry agnostic approach. So maybe we'll find out in the next 3 to 4 years. Right, okay. Just a quick comment on like some of the issues that off-the-shelf models sometimes have. This is not just true about CalOSim, but a lot of physics sim is that they have, so they're not always looking to model the entire distribution, right? So this is a BE GAN, which came out quite a few years ago now, but I really liked this comment in the paper that said, we see fewer older people in the generated images than in the original images. We also see more women than men, and we don't see things like cigarettes. So this is the training data set. This is the training data, sorry. And this is the generated images. So this paper at the time generated very nice images for the time, but apparently, yeah, more women than men. So things like that. So it can, what the industry is optimizing is not always the same as us. So they don't necessarily want to generate the exact probability density that we want to do. And then the other thing is, for example, pixel intensities are not something they care about. This is Einstein, but this is also Einstein. For them, they don't care. But for us, the amount of the intensity per pixel would be the same as the energy in a calorimeter cell, or yeah, so things like that. And then if you just take off-the-shelf model, they don't model these kind of energies. So the width of these distributions tells you the energy distribution, and what you expect. You want this is not an error bar. The width of the black line tells you the standard deviation, and you want the GAN and the VAE to catch the standard deviation, and it didn't in the original studies. Eventually, we had to come up with physics-based losses or physics-based preprocessing to improve this. But yeah, and then you see this also in when you're doing GANs for simulation of like physics, like any like processes that like some of our theory colleagues in Heidelberg found that simulating events also, the model would not be able to capture sharp peak structures like the mass of a particle, which is sharply peaked. And you had to add physics-based losses to improve those distributions. Yeah, so this is in fact the plot I was talking about. So by default, it kind of smooths things out, and then you have to add one of the Breit-Wigner, Gauss, or some other loss to make this distribution reappear. Yeah. So they solved it. I mean, this one, they used an MMD loss. This is quite a long time ago. So yeah, you have to use, like, you have to know that there's a peaky structure and you have to put a loss for it. So it doesn't come for free. They know, they did it with maximum mean discrepancy. This was quite a long time. It was like 2019 or 20, I think. Yeah, but they did it with the maximum mean discrepancy loss. So they specifically look at the distribution of this variable for simulation and data, and if there's a difference, they penalize for it, in addition to the regular GAN loss. Yeah, and since then, like, even the original GAN paper had an energy loss, and every subsequent this kind of paper either has a pre-processing that removes the energy, so normalizes things. Yeah, even our diffusion model from just a few months ago, we had a physics-specific loss to get the mass of the top. Yeah, okay, so just to show that, yeah, you can solve these issues, just you need to have a specific loss function that focuses on getting these kind of energy distributions or mass distributions, right? Yeah, so for the GAN, that's what we did. We got a second discriminator that only looks at the energy. For the VAE, there was some pre-processing that was done to factorize the problem. So you generate the total energy separately, and then the VAE only generates the shapes, so normalized images. Another question that often gets asked, like, it's important to take a step back and think, why are we doing generative models? If you're going to train a generative model on this training data, why not use the training data itself just reuse this training data for simulation? There are a few reasons. One is just that storing the training data in memory and pulling it out and using it is not memory efficient. So you can think of neural networks as a very smart compression of information. Like, you can think of ChatGPT, it seems like a big model, but considering it's memorized the entire internet, that's a pretty good compression, right? A few gigabytes. The other thing is, of course, it can interpolate between training events, which I showed you earlier. So it can learn at 10 specific energy points and then generate continuously. And this interpolation is not just simple energy, it can interpolate in other phase space as well if you need. The final thing is, I think, the most interesting, is that neural networks have this self-regularized nature, which means that you will often find that it lets you smooth over the statistical fluctuations in your training set. So sometimes you can actually get a little bit more mileage than your training set itself. Let's see an example of that. So there's this very nice paper called Gamplification, which explicitly showed that you can train a GAN on a training set, and then the GAN will be able to generate for you more events than the training set itself. And they will have nice statistical properties. So they did this first. The first paper was, they showed it for a 1D camelback function, this one, where so you train on 100 data points, and then the GAN can generate. So the orange is the generation, the truth is in black, and right. Okay, yeah, so the truth is in black, and then the samples are the 100 events that are sampled from the truth, which is in blue. So you can see that the blue has more statistical fluctuations than the GAN generated sample. So the GAN is able to smooth over these statistical fluctuations, which is fascinating. It's something in the community we knew, but this was the first paper that actually showed it in like in very clear way. And so then they said, like, if you were to calculate the mean square error between the truth and what the GAN generates and what the samples give you, and so on, then the samples itself, they have a certain mean square error with respect to the truth. So there's an error bar here, because if you choose 100 samples randomly, each time you're going to get a different sample. So this is the error bar coming from that. And then the GAN actually blows past that. And if you generate about 100 samples, the GAN has an error similar to the samples. But then you can start generating more than the training set. So you can generate 1,000 samples, and then you get a mean square error smaller than the sample itself. And you can go further, and it plateaus at some point. And if this makes you uneasy, it shouldn't, because it's not doing magic. if you were to know the camelback function, you knew that this was a camelback function and you fit it on the samples, that's the best you can do, because then you've added all your inductive bias. Inductive bias means you know that there's a functional form and you fit it, and then you see that that does even better than the GAN. So this is the best you can possibly do, right? So the GAN, by being this self-regularized function, is approaching the inductive bias, which is if you knew the actual functional form. So it makes sense that the GAN would do better than the training samples, but worse than the functional form itself. I'm going to pause here because I find this really interesting, and I'm sure there will be questions. Yeah, 100 points is very small, but it's also such a simple function. Right? It's like a Gaussian, but two of them. Yeah, that's a good point. So does this only work for this two-dimensional camelback? If it did, then that would be a useless study. So there is a follow-up to this paper where they do it for calorimeter images as well, and it's true there. I don't think I have more plots from this paper, but you can see oh, maybe I do. No. So the thing is here, we see that, okay, the GAN can generate about 5, so sample is 100, and GAN effectively, the GAN produces statistics that is similar to if you had 5 times the training sample, right? The mean square error goes down until 500. So what that means is there's a 5x amplification power. And this 5x you know only because you actually can generate 5 times the sample and see at what point the GAN saturates. This you can only do in this toy problem. In a real problem, you can't just generate 10 times more or 100 times more data to see. If you could, then you would train it on 100 times more. Right? So even though there is this amplification power in the real world, you don't know how much it is. So it could be 5 times, it could be 1.5 times. So even though you know the GAN can probably go more, you don't know by how much. So you can't, so this is interesting, it's an interesting statistical study, but we can't use this to do anything at the moment because we don't know when the GAN saturates in a real world scenario. Yeah. Outlier. Can you explain, or what do you mean? Yeah. Yeah. So here, are you talking about the tails, or do you really mean outliers? Tails, okay. Yeah. Here, I mean, from I see that the tails are modeled well. In practice, I've found that sometimes they are and sometimes they aren't. And indeed, so the Heidelberg people often say that the tails undershoot, GAN undershoots at the tails. In my experience, it goes both ways. So I don't know if we can make a conclusive thing, but yeah, I guess often you might have that it produces more events at the bulk and less at the tails or something. And for that, flows are much better. Flows capture the tails a lot better. That's right. That's right. Yeah. Very, yeah. Okay. Okay, interesting. So you're saying that the GAN is making this assumption that the function is smooth, and if it weren't smooth, it wouldn't work, and that's true. That's true. If it was some crazy function, the GAN would try to smooth it out, and it would be wrong to do that. Usually, though, I think things are kind of smooth. And in fact, this is why the GAN does not capture the sharp, what was that, the mass of the W or something. The reason it doesn't catch these sharp peaks is because, yeah, it assumes smoothness, and it goes wrong sometimes. Yeah. So as long as you believe things are not going to be crazy shaky, then I think this regularization is reasonable, and then sometimes it won't be. The other thing, similar to what you were asking, is what if, so here I'm comparing the samples themselves to the GAN, and in the sample I'm not applying any smoothing. So maybe you're saying, this is unfair. what if I used a kernel density estimator, which also has a smoothing function? And in the paper, I don't have plots for this, but in their paper, they compare also to a KDE, and they show that the GAN actually does a better smoothing than the KDE. So it outperforms simple smoothing functions as well. Mm-hmm. Yeah, so there's okay, so then I would suggest to look at their follow-up paper on Calo simulation, which is a physics data set. So there, it's a real problem. And again, they see it's called Calo amplification. The people in Heidelberg love to come up with funny names. Yeah, but yeah, I would encourage you to have a look at that paper. It's very interesting, and also they find there. I think they do the comparison with the KDE, and they show that the GAN is able to amplify more. Yeah, but it's true. If you know you have some sharp thing, the GAN will not catch it. I don't know if I have anything else. Oh, right. So okay, yeah. As I said, we don't know how to without generating more data find out what the actual power of the GAN is. The last thing I can say is, I think I've mentioned this before, that evaluation of generative models can be challenging because there are plots and plots and plots and plots and plots and plots, right? And at some point I felt like I was doing a PhD in plot evaluation. So we want to automate that, and we don't want to become like what ChatGPT is doing, is like paying people very little to uh, to this is how they're making their ChatGPT not say crazy things. They're paying poor people to uh, filter out toxic stuff. So we don't want to be those people. So there's an active field of research going into how to automatically quantify the performance of generative models, so things like Wasserstein distance and Frischle distance or likelihood ratios. And I think I talked about this on Friday, that there's this nice paper that compares toy cases distortions as well as sort of a physics data set, and you find that there are the Frischle Gaussian distance was one of the most promising ones to automatically quantify the performance of networks. Okay, yeah, that is all I wanted to say about generative models in high energy physics, and you will find all kinds of new applications like anomaly detection and simulating extra background in your analysis and so on. Right. Is Elham here? Yes. You want to? Yeah. So questions? Yeah. Yeah. Yep. Yeah, this was I think the first attempt. So it was not even HGCal, it was the prototype HGCal, which was what was available at the time. So they had I think the name of the paper is very precise. So I'll send you the paper, but okay, yeah, they trained a GAN, and the GAN was a DC GAN style, so lots of convolutional layers, and the idea was to simulate, I think, single particle showers. Sorry? I think so. But okay, the link is here. I have the slides, so I will just send the link to you, and you can have. I'll do that. Yeah, I'll do that. Yeah, there are many. Alice has something. LHCb even trained on data directly, which is very interesting. Yeah, every experiment has done something very cool. Yeah. I mean, at the moment we have nothing, so you can dream as big as you want. But yeah, I mean, why not? Why not? Like, if you can have one model that can generate pictures of the sky and the moon and cars and everything, right? Then why should we not dream of having one model? Let's start with our field. But sure, like if we can put out a foundation model and someone from Astro picks it up and fine tunes it, I would be very happy to see that. Okay. I've left you very little time to talk about anomalies.
Okay, so very last 5 minutes, we should be able to do it. Just I wanted to introduce a problem that's there in the notebook, such that that's why we added like 2-3 slides, so that you know about the problem and later on you can do it on your own time. So this is anomaly detection in particle physics, and particularly the collider physics. I don't know if you have seen this problem or not before. So the challenge here is that we want to detect signals which are resonant signals from the background. And background here, the assumption is this is a falling background. So you can think about this is a dijet kind of process, 2 jets, and this is a dijet distribution, dijet mass distribution. So the signal here, the assumption is the signal should appear as a bump. And what we traditionally do, we essentially choose a discriminant observable, often the mass, the MJJ. We define sidebands, which are basically the low signal concentration, and we fit the background in the sidebands, and then interpolate the background in the signal region, and then you do a statistical analysis normally that you do in Atlas CMS. Now, it relies only on one observable. That's the first limitation. So you're losing out lots of other information you might have in the data set. So a multivariate approach could be useful. So that's kind of what many people are exploring in the experimental, now in the experiments, CMS, Atlas, both. In Atlas, we have 1 or 2 papers out already. CMS paper is also out now, I think. And there are lots of methods paper outside, independent of the experiments. So here, the idea would be, we have the data sets, the MJJ data set. Instead of looking at the MJJ distribution only, there's a summary statistics of MJJ distribution, which you often create a histogram and do a likelihood fit. We want to look at multiple variables. Let's say there are n other variables of the same events. We want to define the sidebands. This is just one schematic, like the challenge that we're talking. We want to define the sidebands whichever way you want. And then essentially and also the signal region, and essentially you can slide the signal region to do a realistic search in an experiment. And if you have all these multiple variables, we want to estimate all the variables in the sidebands and then interpolate them to the signal region. Now the question is, how do we want to model them? So here comes the generative algorithms. So the notebook that we have some examples given in the notebook. So I will tell you about the data set. The data set is LHC Olympics 2020 Anomaly Challenge data set. Maybe you have seen it, or maybe you might not have seen it. The link is there. In the notebook, also the link is there, how you get the data set. If you search online on LHC Olympics 2020, you should be able to find it. The target signature here is a BSM particle decaying into X and Y. Those are also BSM particles and decaying into decaying into quarks. And there are, the background you expect to have like without any substructure. It's mostly kind of no clear bump anywhere if you plot a distribution of mass of the X and Y. In the signals, they're given 2 types of signals, through 2-prong and 3-prong. So in the 2-prong signals, the X and Y, which is coming from a particle like Z prime or W prime, of a mass of 1, I think they have masses of, written here, masses of 500 GeV and 100 GeV. So for X and Y, and then the Z prime is giving to 3.5 TeV. So it's 3.5 TeV mass particle decaying into two particles, X and Y, jets basically in the experiment, either having 2-prong structure or 3-prong structure. In one case, X and Y both decays into 2 quarks, and the other case, X and Y will decay into 3 quarks each, right? So I'm just showing you some just some plot of those data sets that are given. So this is a background, which is the field histogram. If you look at the signals, the 2-prong and 3-prong signals, they should look like something like that. And if you just merge the signal and background, they should appear like that. Well, in reality, that's not the case, right? This is what the total number of events has been plotted. But this is just for visualization. So you expect to see a bump here, and your challenge is come up with a model which will estimate the, which will enhance the signal sensitivity, essentially. Some more plots of the data sets. Here we're showing the signal background. This is leading jet PT and leading jet PT for both cases. You can see clearly there are some differences between the signal and background. If you plot the jet mass distribution in the 2D jet mass distribution, here in the leading jet PT versus leading jet PT 1 and what's the other thing? I can't read. Leading jet PTX and leading jet PTY. Those were plotted here. And then here, the leading jet mass and the subleading jet mass. So in signal, these are very clear. We have 100 GeV and 500 GeV. So you see 2 dots, 2 basic, very bright points. For background, there is no clear structure. So you will not see any points. So this is just to show you the data set. Some more variables if you draw them in one-dimensional. Now the challenge is, given this data set, you have to come up with an idea such that you can enhance the signal sensitivity. That's basically the challenge. I'm not going to go more than that here. I'll show you the part of the code, example code, which are given already in the notebook that you were working with earlier today. If you scroll down to the section 3, we have this anomaly detection data set, some description of that, the GitHub page, the web page where it also has some description, the link to the data set, how you get the data set. If you go to this page, they have also the Zenodo link. And then there's some pre-processing script here. And at the end of the day, there are some generative algorithms used here. You can use something else though. But in this code, there are some normalizing flow models used, and the plots are not plotted here. So you try it and you can modify it. There are already some papers out on the same method. So with normalizing flow, there are already 2 or 3 papers out, which shown that then using some of the variables, you can model the background very nicely in the sideband and interpolate the variables in the signal region, and you can, by that way, you can enhance the signal sensitivity for those kind of resonance signals. So that's what I wanted to introduce. We will not go through the notebook since we don't have time today, but that's mostly it of the generative models. If you have any questions about or any clarifications about the problem, let me know. Otherwise, you can also have a look later on your own time. So any questions or any clarification needed? This is for resonance signal hunt. But the signal models they give, those are resonance signals. But I think the backgrounds are still fine. If you want to do some, non-resonant search, you need to simulate some events. Yeah. Yeah. You have 3 unknowns, but the X and Y, you can estimate, you can reconstruct them as jets. Yeah, you don't know exactly. You don't know, and there are some similar searches in Atlas now and CMS maybe. I don't know. Yeah, in Atlas there is some one published result. So you then all the visible. You mean? No, in this problem, this is much more simplified. These are all jets. The Atlas search we did, it's semi-visible jets, and there are also some other final stages ongoing, not out yet. But so there are, you could dijet is the most simpler case. So everyone start started tackling that problem first, but now that it's understood a little bit better, we have other analysis ongoing. CMS did this analysis, digit analysis, very recently out. I think they used 5-6 methods which are published all together in the same paper. In Atlas, we have one paper out with the method called Koala. Second paper is still ongoing, but yeah, CMS did 5 or 6 methods in one paper, which is out now. Yeah. Okay, so that's mostly it. If you don't have any more questions, we'll just wrap it up here, and then you'll have 15 more minutes. Take a break, and then we'll have the